So the characteristic curve for a diode, and this is 0 volts, this is forward bias, this is reverse bias. And it starts off, we'll have a little bit of conduction, and then if it's silicon diode, when it hits about 7/10 of a volt, it'll come up and it will angle up. It won't go straight up, it will angle up. This is the characteristic curve for a diode. Now on this side, when we reverse bias it, you should see a little bit of leakage current. And then when it hits around the breakover voltage of lower, it's going to break over like this. And it's going to slant too. Now what causes the slant? This is the actual R of the diode itself. So everything's got a little bit of resistance, and if you put more current through it, so we use approximately 7/10 of a volt, but that's an approximation, right? The more current you put through it, it'll drop a little bit above that, and the less you drop, it might even go a little bit below. That information is some of the information in the data sheet. Basically, what they show you is they show you the VF, we call this the VF. So when we look at the data sheets, that's what we're going to look at. We'll look and see what the VF rating of the diode is. And it'll give you the VF is going to be at the rated current. So I think we're going to be using a 1 in 914, and I don't remember. And I don't know what the rated current is in that. The ones we're going to use for this lab. Then we're going to move into the 1 in 40,000 series that we looked just a little bit on the data sheets the other day, and those are all 1 amp. So what we're going to do, guys, you're actually going to graph this out. So what we're going to do, now if you look at the if we look at the actual circuit, what's going to be here, first we don't measure resistors, we use their color-coded values. Don't worry about that. We understand that our calculations will be perfect, but now we understand that our measurements are not going to be exactly the same due to the tolerances of the resistors. Just X it out just like I did right here. Oh, I'm sorry. Let me put it over here. That makes a little more sense, right? Yeah, we're just going to X that out. We're not going to measure anything. Here you'll just use your DMM, your digital multimeter values, because we're going to see if the diode is good or bad, right? That's one of the things that we're looking at here. Now the problem is the problem that we have is that when you look down at the chart or at the circuit, this is the actual circuit, and anytime we see a symbol through a component, what does that mean? We see an arrow drawn through a component, what does that mean? So anytime we see an arrow drawn through a component, what does that mean? This is. I can't remember. I don't know. On the tip of your tongue. Okay. Any symbol. So back in DC, you had the symbol right here, right? Here we got this right here, and then we got the symbol like that. So what does that mean? That it's broken? No, no contact. No. No. This is variable. So this is a symbol for a rheostat. This is a symbol for a variable DC power supply. So this is the one you got your knobs on over there, right? So we have 3 fixed power supplies on our trainer. And then we've got one that's got knobs where I can adjust the positive power supply and the negative power supply. So that power supply should have that symbol right there. So anytime you see an arrow drawn through a component, it means it's what? Variable or adjustable, right? I need to make sure they teach that in DC. So the problem with most variable power supplies is we are never ever we're not able to adjust them down to 0. So our variable power supply, about the minimum voltage we can get out of our variable power supply is around 2 volts. Now when I look at my chart, what's the first voltage we're supposed to put on our diode? Yeah, 450 millivolts. And now we're going to have to put a resistor on this thing because as soon as it cuts on, it acts like anything above VF is going to be like a short circuit, right? Understand? And what size are we using there? We're using a 330 ohm. And then we're putting our diode in forward biased. So what do they have? Yeah, forward biased. So if my power supply puts out a minimum of 2.4 volts, how am I going to get 450 millivolts? This is a variable. This is it.
Oh.
What component can we use to adjust the voltage? Capacitive component. I did a lab on this in DC. What's that? Yeah, potentiometer. So what we're going to do is we're going to vary this. We're going to vary the diagram a little bit. This is the correction we're going to have to make. We're going to have, y'all know the pot, right? So we're using these guys. And then we got a knob on it. And it's real easy to see. Normally, this will be one side. This right here, this is what's important. This is what we refer to as the wiper. That's where we're going to vary the voltage. So what we want to vary the voltage across, we come over here and we put it between the 2 outsides. So this is pin 1, this would be 2, this would be 3. So up here, this would be 1, this would be 3. And then this is the wiper. So this is where we're going to vary the voltage at the wiper. Everybody understand that? Yes or no? It's a voltage divider. So what it is, and we're using a 10K pot. So what we can do with a 10K pot is we can do this. If we adjust it all the way up to the top, we end up with this right here. And if I put, let's say 10 volts right there, and I measure with my voltmeter right here, what would it measure? What would it measure? What would my voltmeter measure? 10 volts. Good. Now, if we come over here and do this, this is when we're going to adjust the pot. So this is what the pot turns in. So what I just showed y'all, first of all, is if we had the wiper all the way up at the top. If I put the wiper all the way down at the bottom, we end up with this circuit right here. I'm sorry. If this is 10 volts, we end up with this circuit. You end up with this circuit right here. So what would my voltmeter measure there? Yeah, it measures it. It's going. Our voltmeter is going to measure something, but it's going to measure 0 volts, right? Well, if I put it in the center, if I put it away from the top, so if we move it all the way to the top, we get whatever voltage we put across it. If I move it all the way down to the bottom, I get a 0. If I move it somewhere in between, we get a 2 resistor voltage divider. So if this is 10K and I come up here and I put 5K right there and put 5K right there, and then I put my meter right here, what would it measure? It measures 5 volts. But what if I came over here and put, if I adjusted and get 1K up here, down here I get 9K. I hope not. Wait, no, it's not going to be the full 10 volts. This is where I'm putting my voltmeter at. What's that? Should read 9 volts because it's 9 tenths, right? You understand? But we can, well, what if I set this at, 1.2K and I come down here and set this at 8.8K, then we would just solve it. So what we can do is using that pot, I can set my voltage anywhere from 10 volts down to 0 volts. Any voltage I want between 0 and 10 volts. It's as accurate as I can adjust it with my hand. Right? You understand that? And that's what's nice about a potentiometer. It's a variable voltage divider. I can set it anything between the watt, the top, and the bottom. So if we come over here now, instead of hooking it directly up, so this is the way our circuit is going to look at that. Is we're going to come off our power supply, our variable power supply. And then this right here is what they call ground, but it's not ground. So this is going to be the black screw, right? Understand that? And then I'm going to come off the plus power supply up here. In fact, we could come off the 5 supply, but I think the 5 volt might be bad. Then we're going to come over here and I'm going to run this to a potentiometer. Then I'm going to take this. This is going to be my 330 ohms. And then my diode's going to be right here. And my diode's coming.
So with the 1 and a 3 on the actual.
Yeah, this would be the 1 and 3. That would be on my pot. So I'm looking at it from the bottom. This would be 1. This would be 2. This would be 3. Now what you got is this is where we got right here. We got 3 wires coming up because we got to put this into the breadboard, right? So this is the pot, right? 1, 2, 3. This is the wiper. So this is going to go to the 330 ohm resistor. This right here is going to go across your power, the power supply on the train.
So both of them are going to go to the power supply. You got one going to the actual power supply, the other one.
No, you got 2 going to the power supply. So here's the circuit. I got it. So here's the circuit. Here's my power source. I'm sorry, this is 3, guys. That might be why I'm confusing. This right here is what? 2. So the pot's going to wire across the power source, and then that way I can get anything I want. So what's the maximum voltage we're gonna need? 0.75 volts, right? So over here we probably need to set this. We can set this to like 3 or 4 volts. It don't make a difference. We just don't want to exceed wattage rating of the pot. And now what I can do is I can move this pot right here, and I can set this to get what? 0.45 volts over here, or 450 millivolts. And then what we're going to do is we're going to measure the current. Well, we're not going to measure the current because normally we have to measure what do we mean by measure the current? That means I'd have to break the circuit. I'd have to put my ammeter in there and measure it. I don't have to do that, guys. I got a 330 ohm resistor. And I know I is equals what? Okay, so that means I can calculate my current. So that's what we're doing. Right here, we're measuring the voltage drop across R1. You see that in your table, right? And we know the size for R1, right? You understand that? Yes or no? So all I have to do is take what? To calculate I'm going to take the voltage drop across R1 that I recorded in my chart, and then I'm going to divide that by 330 ohms, and that will give me I through the diode. Why is that I through the diode? Because they're in series with each other. And the current is the same in a series circuit, right? So if I calculate the current flow through my resistor, then I know the current flow through the diode. And then what will we do? Once we do that, we'll adjust it up to 0.5 volts across my what? Across my diode. No, because we're going to see where it actually breaks. We're going to see where it actually starts conducting. So all we're trying to do is see where the diode starts conducting. So when I actually come up here and draw my table, which is on the next page, which is on the page before the question. So we got this graph that we're going to be working with. So this is the graph. And so I've laid it out for you. A lot of people have problems with this. And what we're going to do is we're literally going to end up drawing this guy right over here. We're going to start off, we're going to have a little current, and eventually it's going to shoot up and it's going to come up at an angle. That's what we're doing. We're actually drawing the characteristic curve for the diode. So what we're going to do is we're going to slowly increase the current. So there's 5 milliamps right there. Okay. 1 milli, 2 milli, 3 milli, 4 milli, 5 milli, all the way up to 15. And what we're going to do is we're going to, this is in milliamps by the way. Then we're going to come up here and chart this, and we're actually going to see the characteristic curve for the diode. So no, we're not, but we should see it start conducting around 0.7 of a volt, right? You understand that? Should see it conducting. Yeah. Yeah, but this is not for this one. This is for this one right here, where I'm going to do this one. I'm going to do this. So here we're going to deliberately break the diode over. So we're going to mark this out, and we're going to do 30 volts, 60 volts, and then 100 volts. So we're not going to do this. So that's what all these power supplies are up here for. And we're literally going to break the diode over in the reverse direction. Why aren't we going to damage it? Because we're going to put a 1 mega ohm resistor in series with it. This says 10. I'm going to put a 10 mega ohm resistor in series with it. So when it does break over, there's not going to be enough reverse current through the diode to actually see it damaged. That makes sense? So we're going to do this as a class. And then what I'm going to do is I'm going to get a soldering iron. I've got it over here. And I'm going to heat this thing up, and we should see the leakage current go up, right? You understand? And then I'm going to cool it down with some from freeze spray, and you'll see the reverse current drop down real far. And that's what controls the leakage current of a solid state device is the temperature. In fact, we got a solid state device called a thermistor, and that's what it is. It's a semiconductor. The semiconductor, the current flow through a semiconductor is controlled not only by its resistance, but how much heat you run in it. And this is why semiconductors are going to be rated at a temperature too. So that's one thing we'll look at right off the bat. So we can't operate them above a certain temperature, or the leakage current would get so high and it would damage the device. That's why we don't want to operate them above what they call the reverse breakover gauges. So this is the lab. This is the actual modified. These are the 10K pots right here that we'll be using. Okay. And we're gonna do this as a class. We're not gonna do this individually, like I said, because we gotta get up above 100 votes to cause this thing to break over. That's lethal. So that's why I've got all these power supplies stacked up here. I'm gonna hook them up series 80. So series 80 means that y'all actually did that in DC too. Series 80 means your voltages are added together. We can do that with batteries, guys, or we can do it with any power supply. We just say, so and I'll show y'all that. So I take the negative out and hook it up to the positive, negative, positive, negative, positive. And then, so I've got 4 power supplies. We can get 30 volts out of each one of those, about 30 volts. So that means I can get 140 volts out of these 3 that stacked up together. So we okay? Who left and didn't